Hi, welcome to this lecture on graphs. My name is Dr. Ritesh Ajura. So what is a graph? A graph is a pair, a set of vertices and a set of edges. So V is the set of vertices. E is a collection of edges, all right? The vertices in a graph, this is a picture of a graph, the vertices would be these circles. So let's just put a little circle around. This is an example of a vertex. This is an example of a vertex. In this example, the vertices are containing airport codes. And the edges, right, that's your set E, are these lines between the vertices. Okay, so a graph is nothing more than a collection of these vertices and a collection of edges. But when we specify the graph, we specify what is in the vertices and what is in the edges. Well, not only what is in the edges, like these numbers, but also to what vertices does the edge connect. So in this case, this edge connects to LEX and ORD. And in this example, the vertices, as I've said, is airport codes, and the edges are the distance in kilometers between these airports. So you can see, oh sorry, not in kilometers, I think it's in miles. My point is that these edges can store information, and in this particular example, we're trying to store the distance between airports. We're trying to store that information so that we can perhaps find the shortest route from one airport to the other through these various different paths. So suppose we're looking for the shortest distance between SFO and MIA. Okay, so let's take all of those markings away. What we would then do is we would start here, SFO, and we would have to consider all of the different paths that move from SFO all the way to MIA. So here's an example of a path. So we start off at this vertex, we can move to ORD, and we can move to PVD, and then we could move to LGA, then we could move to MIA. Okay, here's an example of one path. Another path, let's look at another example. Okay, that doesn't work. Another example would be if we move from SFO to LAX. Then we go to perhaps, I don't know, you go to ORD, then DFW, then LGA, and who knows, we decide to go back to DFW because you could possibly do that, and then go to MIA. All right, so what you need to do in that case is add up all of the different weights on these edges to find out the total distance. This one you will times by 2 because we went twice. We went first there and then we came back. You would have to add up all of these values, which I've circled, to give us the total mileage between airport A and airport B. So this is what graphs are all about. This is what they can represent. This is just an example of what graphs can represent, but obviously there's a host of examples. Graphs are in fact very easy to understand and are extremely powerful in computer science. So let's be a bit more specific about what's the different kinds of graphs you can get. So you could get different kinds of graphs. Like I said before, your edges can have certain properties, your vertices can have certain properties. And so let's speak about these. So you can get this notion of a directed edge. A directed edge means that, well, before in our example, we found that the edge, there was no direction from one node to the other, right? It was just we could add a direction by putting an arrow in. And then we can say, well, the edge goes from LAX to HNL. Right? There is this notion of direction. So if we have direction, we refer to the edge as directed. And all it means in our representation is that now, instead of just having a pair, we have an ordered pair. So an ordered pair means that this comes first and this comes second. This is very important. So we're going from U to V. The first vertex U is the origin, and the second vertex V is the destination. Okay. And an example of this is a flight. Okay, you're moving from one airport to another airport. It is possible that you could go from the other airport back, in which case you could have a direction going this way and a direction going the other way. So here's an example of a directed edge. Notice the difference is this arrow. Here we had ORD to PVD. The direction here is very specific. It's ORD, comma, PVD. From U to V. Here it doesn't matter. You could have PVD, ORD. I need to get a pencil. Or PVD to O. Oh, I just already wrote that. Or ORD. So you could go either this way to this way, or this way back that way. ORD, comma, PVD. Okay, hope that makes sense. So if you have a directed edge, you could have an undirected edge. So here's an example of an undirected edge. Yeah, this is an example of an undirected edge. Here you have no arrow on this line. If all of your edges in the graph are directed, we refer to the graph as a directed graph. Okay, so directed graphs, you have a graph, so you can have a node and an edge that's directed to another node and an edge that's directed to another node. Notice that in our definition of trees, which was the previous lectures, you had this notion of direction in a hierarchical sense, and there was this thing that every node had to have one and only one parent. Okay, but notice this node, it's either a directed graph. This node has two parents. It has this one and it has this one, and it could have another one too. In fact, you could even have an edge like that. So, and the difference between a tree and a graph is that trees, every node has one and only one parent. And in a graph, you can have many parents, more than one. So that's the difference. An example of an undirected graph, well, just go to the previous slide. You'll see here's an example of an undirected graph. You could make it directed by simply adding these arrows in. Like here, we've made this edge directed. You could make this edge directed, and this edge directed, and that edge directed. And if you do this for all of the edge, you will turn this into a directed graph. I hope this makes sense. So what are the applications of graphs? Well, I've told you that graphs are very powerful. In computer science, many architectures, especially in artificial intelligence, are done using graphs. We find the neural networks in artificial intelligence or machine learning are represented as graphs. We find in probabilistic graphical modeling, things like Bayesian networks are represented as graphs, and these are extremely powerful tools to perform inference. The latter is one that I'm interested in. It's part of my research interest. Bayesian networks, that is. So there are also applications in electrical engineering. You could represent a printed circuit board as a graph. You could represent integrated circuits as a graph. You can represent transportation networks as a graph. As we've seen before, the flight network on the first slide. A highway network where you have different areas and you have roads between these areas. So that can be the roads can be represented as edges, or the roads can be represented as vertices. Really does depend on your perspective and what you're trying to do. In computer networks, we have local area networks, which can be represented as graphs. Here, your local area network, you have your computers and your LAN cables that go between the different computers or servers or whatever the case might be. You can represent it as graphs. Well, perhaps the speed of the cable could be the weight on the edge, represented as an edge. Perhaps some information or description about the type of computer can be represented as vertices. Like I said, it really does depend on what you're trying to look at or what you're trying to represent. The internet itself can be seen as a gigantic graph where nodes represent various servers, Internet of Things devices. You have even your smartwatches, or whatever the case might be. Everything, all of the devices, the end users, and the connections in between can be represented as vertices and edges, respectively. The same goes for the web. So those of you who have done databases may also been introduced to graphs in terms of the representation. You could have the cardinality between different databases as the edges, and perhaps the tables as the vertices. And your vertices in this case are much more structured, but my point is that it doesn't matter what you're representing. You can represent a table in databases. You can represent the vertex as a computer, or as an airport, or as a cat, or as an animal, or as a car, or whatever the case might be. My point is that a object in whatever form can be represented as a vertex, and your and another object in whatever form can be represented as an edge. So there's no limit here. It just depends on how you are representing your problem. And these are nice examples. Here's a nice picture of a network, and here we see how the computers are your vertices. These are the vertices, and your edges are these lines. So we see here the edges aren't explicitly storing anything. So your vertices are storing things, quite obviously. There's servers here, there's routers, there's LANs, there's PCs, and other end devices. We see that those are being represented, but we don't see any representation or any auxiliary information on the edges. We can see that the edges are coding between which vertices does it exist, but it's not encoding any information. And a graph like this, where the edges are not containing any information, is called unweighted, because it doesn't carry any weight. Unweighted. If it had information on it, we would refer to it as weighted. Like perhaps it had the speed of this line, maybe 70 kilobytes per second. I don't know. This one was 60 kilobytes per second. This one was 50 kilobytes per second. Maybe this was a wired network. This was 500 kilobytes per second, or perhaps, I don't know, anything. In that case, you can store this number as a weight on the edge. So let's get a bit more into the terminology here, because like I said, graphs are very powerful. And if you want to represent a problem using graphs, then you would need to know the terminology. You always need to know the terminology. So looking at this graph, here's an example of a graph. On your right hand side, you find a graph. Here's a graph. And on your left hand side, you find descriptions about the terminology. So let's start off with n vertices, or endpoints of an edge. So U and V are the endpoints of A. This is your A. U and V are on the end of A, on either end, and we refer to that as the endpoints. We refer to edges incident on a vertex, right? So let's look at the example. A, D, and B are incident on V. Okay, so here's A, here's B, and here's D. They are incident on V. Okay, they're connected to V. So notice endpoints is on either side of the edge, and incident are those that are connected to a vertex. So these are the edges connected to the vertex, therefore they are incident. And we get the notion of adjacent vertices. So an adjacent vertex, we say that two vertices are adjacent if there is a direct connection, right? So a direct connection meaning one edge between them. So we see U and V are indeed adjacent because there is A and only A connecting them. U and X are not adjacent, okay, because there isn't a single edge that connects them. If we had this edge here, maybe it was Z, then the U and X would be adjacent. U and W are adjacent. X and Y are adjacent. X and Z are adjacent, and so on. So that brings us to the degree of a vertex. So a degree of a vertex is the number of edges that go into it. Now you get the in degree and the out degree in directed graphs. So in an undirected graph, we just have this notion of a degree. And there we're just counting the edges on a vertex. So let's look at X in this example. How many edges are going into X? Well, not really into X, but how many edges are directly connected to X? So we see this is 1. This is 1, this is 2, this is 3, 4, and 5. So the degree of this vertex is 5. Suppose this was a directed graph. Then we would have a notion of an in degree and an out degree. So if this was a directed graph, then you could have direction in these edges. Now remember, if it was a directed graph, the entire graph will be directed. For the sake of simplicity, I'm only going to direct a few of these edges to demonstrate the definition. So a degree of a vertex, in terms of a directed graph, whenever we will be referring to the in degree or the out degree. The in degree is the number of edges that go into X. In that case, it's 2. The out degree are the number of edges that go out of X. In this case, it's 3. This brings us to parallel edges or multiple edges. Parallel edges are edges that that connect the same two vertices. Okay, so X and Z are connected both through H and I. So these are known as multiple edges or parallel edges. So we see that maybe in this application it's necessary, but in most applications we assume that there are no parallel edges. And the same goes for self loops. We see that J goes from Z all the way back to Z. Okay, it depends on how you look at it, but no matter which way you look at it, it's going to be looping back. If there was a direction here, we can say it goes from Z this way, or if there wasn't one, then we could go from... Now you might think of many applications here, but for the sake of most of the graphs we look at, we will always assume perhaps that, unless otherwise as stated, that our parallel edges and self loops are not allowed. Although it's easy to implement. This is just something that's in special cases. So, continuing our terminology, we now speak about paths. Now, I spoke about paths in the beginning of this lecture, but a path is nothing more than a sequence of alternating vertices and edges. So let's look at an example of a path. So look at this path. We start off with V, this P1. We start off with V, okay? Then we have B, then we have X, then we have H, then we have Z. Here's an example of a path. So it begins with a vertex, and it ends with a vertex. It begins with a vertex and it ends with a vertex. In the next example, we have, let's try another example. Let's suppose we're going with this path. So let's state it. It'll be U first, then C, then W, then F, then Y, then G, then X. This is an example of another path. So we can have many different paths. And I'm sure, as you may have noticed from the first slide, that you could have many different paths between the same two vertices. So if we're going from U to Z, you could have a path that goes like this. You could have a path that goes like this. Oh, it just doesn't seem to change. You could have many different paths. You could have a path that goes like this. You could have a path that goes like this. A path that goes like this. A path that goes like this. And so on. There's many paths that you can actually imagine, and in fact you can show that there's infinitely many because you can always just go back and forth between the two nodes, since there's no restriction on that. Which brings us to the next set of definitions. So we have simple paths and we have paths that are not simple. So if you have non-repeating vertices and edges, we refer to that as a simple path, or else we refer to it as a path that's not simple. So have a look at P1. That's a path that is simple because we have V, B, X, H, Z. None of it repeat. But now looking at P2, which is this path, we have U, C, W, E, X, G, Y, F, W, which means W repeated. Then we have DV. So because W repeated, see W appears here and it appears here. Then we know that this is a path that is not simple. This brings us to the next set of definitions, a cycle. So we know what a path is. A cycle is when we have a circular sequence of alternating vertices and edges. So see, this C1 is an example of a cycle. Here we have V, go into X, go into Y, go into W, go into U, go into V. And then we're going back again to X, Y, W, U, V, and so on and so on. This is a cycle. We have simple cycles like this with no repeating terms. And we have cycles that are not simple. And as you can guess, we have ones that repeat. Great, so now that you know what graphs are, the definition of graphs, the various components of graphs, and perhaps possibly some ways of representing problems, let's now turn our attention to the properties of these graphs. So if we make an assumption that we don't have multiple edges and what is this? Multiple edges and cycles, not cycles, and loop edges, then we can have certain properties. And the way this first property works with both, we have the we can have parallel edges and we can have loops. It just says that the sum of the degrees for every vertex, right, because it's an undirected graph, we're looking at the sum of the degrees, not the in degree or out degree, just the degree of all of the vertices is equal to twice the number of edges. And you can see why this is true. And let's have a look why. Just by looking at the graph, we'll see that it's 2 times the number of edges is equal to the sum of all of the degrees for the vertices. Okay, so let's look at this graph as an example. So and remember, this is now it's a strict equals to, right? Because we have we're looking at the degree versus the number of edges. So for this particular node, the degree would be 3. For this node, the degree would be 3. For this node, the degree will be 3, and for this node, the degree will be 3. So the sum for all of them would be 3, 6, 9, 12. It's 12. That's the sum of all of the vertices. Let's look at this. Let's look at the number of edges. So here, this is an edge 1. This is 2. This is 3. This is 4. This is 5, and this is 6. So the number of edges is 6. We multiply it by 2 to get 12. So that gives us 12. Great. So this is fantastic because now we have a formula that relates the number of edges with the in degree. But it doesn't explain why this is true. So for the proof, we can just look at counting each edge twice. So when we were here, we counted the edges. We counted the edges as 1, 2, 3. Okay. And when we were here, we counted the edges 1, 2, 3. We already counted this one, so we counted it again. This is the second time. When we here, we count the edges 1, 2. We've already counted this one, so we've counted it again. 3, so we already counted this one too. And finally, when we here, we count this one, which means we've counted it again. This one, which we've counted already, and this one, which we've counted already. So in the end, we've counted all of the edges twice. So that's an example of how you could visually prove this. The second property, now we need to restrict self loops and multiple edges. So we don't have parallel edges, we don't have self loops. So now we're trying to show that the number of edges is less than or equal to, the number of edges is less than or equal to this term. So how do we show that? Well, we can use property 1 to help us. In a graph like this, let's suppose we have to help us visualize this, let's actually multiply our 2m here. So we're multiplying by 2 here and here, right, to get our 2m less than or equal to n into n minus 1. Okay, as a number of edges. So this is going to be a bound. All right. So to get this, all we need to do here, to just visually see this proof, is just let me erase this first. Okay, it's just think of it as if you have a general. So here we have 4 vertices. So generally, if we had n vertices, what would be the degree of this? Okay, let's try to work it out. Yeah, it's gonna be the in degree here, right? Is going to be, well, we know that there's n nodes. So that means that there will be a line from this node to n minus 1 nodes, which means that there will be n minus 1 edges for this one, for this node. So the in degree here will be n minus 1. The in degree for the next one, since it's undirected, will also be n minus 1. Since the next one is undirected, it'll also be n minus 1. And for the next node, it'll also be n minus 1. For the next node, and so on. And how many of these do we have? Well, we know that is n nodes, so it'll be n times n minus 1, which is the degree. And by this formula, we get this very nice expression. So this helps visualize it. And I'd like you now to think about what is the bound for a directed graph. Well, in a directed graph, if you have, and you just have to now think of lines with edges, lines with direction. So these edges with our direction. So let's now actually look at that. I'll try to draw it for you. It's funny, when I change the color, everything changes. It's very strange. So you have a set of nodes, and in a directed graph, remember we just said there's no self loops. What is a self loop? It goes from the node back to the node, okay? And there's no multiple edges, no parallel edges, so you can't have that. But in a directed graph, you can have it because it's not the same edge. Okay, so remember, for multiple edges or parallel edges, you have the same edge between the two nodes. But in a directed graph, if you have an edge that points in this direction and an edge that points in this direction, it's not the same edge. Okay, so that is allowed. So thinking about this in that way, you would just now need to count the number of edges with respect to having an extra edge going to any vertex and from any vertex if you have two vertices. So you have a vertex A and B. Let me try to draw it. Just 1 second. Let me erase this. You're going to have, oops. Not too sure about this square, but all right. So you'll be counting it. So if you start here, okay, how many different edges can you make? Okay, how many directed edges can you make? So you could make one here. You could make one here. And this we're just talking about going out of this node. All right, so that's n minus 1, because you could have many others, and another one, and so on. If you go to this node, all right, how many different edges can you make? Well, let's have a look. Okay, so it's going to be from here. You can go back to this node, and you can go from this node to any of the other nodes. Okay, if you're here, then you can go to any other node. So if this would have to be n minus 1. This would be n minus 1, and so we're back to square 1. So you would just be now counting this up. But you have to be aware now that we have an ordered pair. And how does it affect m? The number m. So you need to think about that. Let's now actually make this a bit more difficult. Let's now consider the case where we have not only no multiple edges or parallel edges and no self loops, but let's consider the case where we don't allow cycles. So just to refresh your memory, this is an example of a cycle. So you can go from one node back to the other node. Okay, so if you have a set of nodes like this, it's a cyclic graph if there are cycles. So for example, from here you can go to this one, and you can go back to this one, and then here you can go back to A. Okay, so you can follow a path from A to B to C and back to A. So if you can go back to a vertex, then it's a cyclic graph. Now consider the case where you're counting vertices in an acyclic graph. So here you could have nodes going back and forth, okay, but in an acyclic graph you can't. So consider the case where you're counting the number of edges in an acyclic graph. So let's actually consider that. In that case, you would have a node. Oops, you would have a node. Okay, let's say you have n nodes. So I'm just going to draw a few, but it goes on dot dot dot. You have n nodes. Then what would be the out degree? Suppose you have to assume we're not going to have cycles. So you're going to make it so we don't have cycles. So you could have an edge from here to here, from here to here, from here to here, here to here, and here to here, and an n, so you're just going to say dot, dot, dot. So if there are n nodes and you're going from this node to all of the others, you'd be making a line from this node to n minus 1 edges, so n minus 1 vertices. So let's make that n minus 1. And how about from here? If you're starting off here and you're drawing edges, but you can't draw an edge back to n minus 1 because then it will be cyclic, right? Because you could go from this node to this node back to this node. So you can't draw that. You can only draw a node to every other vertex. You can only draw an edge to every other vertex except for this one. So we can draw an edge to this one. We can draw an edge to this one. We can draw an edge to this one, and all of the other ones. Dot, dot, dot. Okay, so far we haven't had any cycles. So how many of these edges did I draw? Well, it'll be n minus 2 because I didn't draw an edge back to this one. This node. So now suppose we're drawing more of these edges. So let's start with this one. Well, I can't draw one back this way, and I can't draw one back this way. So I can draw one here. I can draw one here. I can draw one here. And I can draw one to all of the other edges out there. So that'll be n minus 3. So think about, we're summing the total number of edges. So I'm just going to say the sum of the edges, m, is equal to, it'll be n minus 1 times, or plus, well, it'll be plus n minus 2. Doesn't this look familiar? Plus n minus 3 plus dot, 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 all the way to 3, 2, 1. So you'll keep going on, and you got to sum this. And doesn't this look familiar? Yes, it does. And I think I'll leave the rest to you. I turn your attention to the edition of Taylor series. So just have a look at the previous lecture on that if you haven't. Fantastic. So if you can sum that, you'll get something that'll tell you the total number of edges for a cyclic graph. Okay, so let's go back and back to the properties. So I hope the slide makes sense, and I hope it makes sense within the other contexts. Like I said before, if you have any questions, please post them on the learning management system or direct it to one of the teaching assistants. They are very good, very responsive, and they know their stuff. Okay, so this is pretty straightforward. This is just the methods for a graph. Okay, so you have a set of vertices, like I told you before, and you've got a set of edges, and we can query on particular edges and vertices objects that are from these sets, or from the class vertex, from the class edge, depending on the implementation. But the accessor methods, okay, suppose you've got an edge E, you can access the n vertices of that. Okay, so remember that if you have an A and you've got a line between B, and these are vertices, and you've got a small a here that tells you the weight of the edge, then if you query on an A, what are the n vertices, it'll give you A and B. So it's a list of 2 n vertices, because there can only be 2 things on either side of the edge, right? So that's on both sides of sum. So you could also say E opposite V. So E is the edge, and you can say opposite V. So that's the vertex opposite of V on E. Okay, well, you can think of it as adjacent. And you can also ask things as, is U adjacent to V? And it'll return a true if and only if U is adjacent to V, or it'll return a false. You can also dereference these edge and vertex objects by using the star, as you've seen before. And there's several update methods. You could insert a vertex. If you're inserting a vertex, then you must make sure that it appears in the collection of vertices. Remember, originally, a graph was defined as a set of vertices and a set of edges. You've got to make sure that it appears in the set of vertices. If you're adding an edge, it should appear in the set of edges. It's inserting an edge. Also, you can't just insert an edge. You have to insert an edge with respect to vertices. So it goes between 2 vertices. You can erase a vertex, you can erase an edge, and also you can just provide a list of incident edges to a vertex, or perhaps a list of all vertices, or perhaps a list of all edges. These are all different examples of methods that you could have for a graph. Which brings us to the implementation. Now I'll show you two implementations and we'll compare the complexity of both of these implementations. So the first is the edge list structure. So in this case, our vertex object has an element. Here's an element, okay? So a vertex object, this is it. It has an element. So in this case, this is the real, how it looks to us, and this is how it looks to the computer. This is the implementation, and this is what it looks like on paper. So you have your vertices and edges as you've seen them before. This is a graph structure, but the edge list structure has special connections, and these special connections are defined by the template objects that come from the vertex and the edge class. So your first object here, which is the vertex, it has a reference to the position in the vertex sequence. So this could be a sequence, it could be an array, it could be a linked list, whatever the case might be, but it stores pointers to types vertex. And that type vertex will have an element, which is this U, okay, in this example, and also a reference back to the position in the collection. So it'll point back. So this is these are all example of vertices. These are representing these vertices. Let's look at the edges. In the example of the edges, you have different edge objects. I'm just gonna remove all of the markings so we can just start off on just make it less busy. For an edge object, you have the element. So let's suppose we're dealing with this A, which is an edge object. So if you're dealing with the A, you've got the A, which is the actual element that's stored here, okay? You have the origin vertex, okay? So pointed to a type vertex. Origin vertex, which in this case is U. Well, in this case, it doesn't matter because it's undirected. So it could be either or. And your destination vertex, in this case, is V. Or it could be U too, because it's undirected, it doesn't matter. And finally, you have a reference to the position in a list of edges. So this is also could be an array or it could be a linked list, but my point is that it's an explicit list indicating all of the edges. So if you want to print out all of the edges, you go to this list. You want to print out all of the vertices, you go to this list. The other way I'm going to show you is the adjacency matrix structure. Now this is, I consider it a much easier way of implementing it just because it's so conceptually easy to understand. So here it is easy as well because you had a lot of experience with creating classes for nodes. So you can just think of this as a node that has a reference to a position in an array and an element, and then you can think of this as an object, a class which has a reference back to a list. It has a pointer to a type node, a pointer to a type node, and it has an element, could be a string, could be an integer, whatever the case might be. So this is also very easy to implement. But the adjacency matrix is used because it's also very easy to understand if you may struggle with all of these other pointers and things. And the basic idea here is that you have an array. So I'll draw it back on this just to make it less complicated. So you have an array. So, I'll draw it with a black paintbrush. And this array looks like this. So it's two-dimensional, okay? You've got a graph. So this is your graph. This is your A. This is your B. This is your C. This is your D. And you have edges. Suppose you have these, okay? So the way we design our two-dimensional matrix depends on the format of the graph, okay? So we have A, we have B, we have C, and we have D. So we have 4 edges. So we're gonna now have 4 rows and 4 columns for the 4 edges. We're going to explicitly label our edges. So this will be 0, this will be 1, this will be 2, this will be 3. Now you could obviously associate the edge with this labeling in a separate array. Okay, you could have like a couple or something that says this is a 0 for this B, or this edge pointed to an edge, and this is a 1 associated with this edge, A, and this is a 2 associated with this edge, D, and this is a 3 associated with this edge, C. Okay, you could have something like that. So in this case, you would have B being 0 in this array. Remember that because it's an array, a two-dimensional array, it's indexed using consecutive memory. So these are all labeled 0, 1, 2, 3. 0, 1, 2, 3. So if there's an edge between 0 and 1, we simply put a true between 0 and 1. So 0 and 1 will get a true, and also if it's true this way, it'll be true that way. So about the diagonal, you should have an identical graph. So let's do it for the next one. So you have A and B is already captured. This edge is captured. Let's capture this one. It's between 0 and 3. So 0 and 3, you put a true there. 3 and 0, you put a true there. Then we capture this one. D and C. So that's between 2 and 3. 2 and 3, capture it there, capture it there. Then we have 0 and 2. 0 and 2. Capture it here, capture it here. 2 and 0. And then we have this one. 1, what is this? This is a 2. So 1 and 2. 1 and 2. Capture it here, capture it here. We didn't have an edge here. Okay. So this would remain a null. And that's the basic idea. So you see that we're capturing the structure here. And if it's an undirected graph, then you would have what it would be identical. This matrix will be identical about the diagonal. So that means that this will be identical to this. It's identical about the diagonal. But if it was a directed graph, then it wouldn't be like that. Because in this case, if you had a directed graph with an edge going from C to B, okay, so this is an edge going from C to B, then you wouldn't have, you would only mark from 3 to 0. 3 to 0. You wouldn't mark from 0 to 3. So this would come out. So now it's no longer identical about the origin. So for a directed graph, we have this notion of arrows. And so we have a direction even in the adjacency matrix. So we did it from here to here. And we see the direction that the arrow takes. We captured the direction in this regard. If this was a weighted graph, then you actually could have numbers. So let's put a 1000 here, or 100. Let's put another number here, 50. Let's put another number here, 55. So if we're going to capture numbers, we can capture between B and D, there's a number 100. And this number occurs between 0 and 2, so 0 to 2. Then instead of putting a true, we can just put in 100. And if we do it this way, because it's undirected, you would need to put it this way as well. I hope this makes sense. This is just a very simple example. I'm trying to build your intuition for graphs. So it goes beyond the slides, but what's more important is that you understand the basics. We can't really do too many exercises seeing this. This is the last week, but I at least want you to walk away with some understanding on graphs, since they are such an important data structure. And the teaching assistants really insisted that I make time for this because it's extremely important and valuable. The final thing I'd like you to look at is the performance. And the performance of these implementations really differ, which is why choosing an implementation based on the application is important. So we see that the performance using an edge list and an adjacency matrix differ tremendously, just looking at this table. For different kinds of methods, you have different space requirements and different and different number, and they have different time requirements too. All right, so let's have a look at these, and I'll try to convince you about the complexity of each of these. So remember that M is the edges, a number of edges, and Vn is the number of vertices. There is a difference. You could have more edges than vertices. Okay, these are now becoming dense. And you could have, if you have very few edges, a good proportion of edges to vertices, very small proportion, then you have sparse graphs. But we'll get into that a bit later on. What I'd like you to take away from this slide is that the complexities differ, and N and M is not the same. They are two different variables. So let's look at the space first. So incident edges. If we're looking for incident edges for a vertex V, okay, incident edges, which means that the ones that are directly connected to it, then in an edge list, we would need to search the entire list of edges to find all connections to V. So we would have to go to each and every edge to find the connection to V. That's how we would find incident edges for V. In an adjacency matrix, if I'm given a vertex, all I need to do is go to the row where the vertex is and search this row for all the T's, or all of the things that are not null. And that'll tell me exactly how many incident edges there are. Okay. In the case where we're looking for adjacent nodes, well, we're looking if U is adjacent to V. Well, if I want to find out if U is adjacent to V in an edge list, I would need to look at all of the different edges. All of the different edges. The list of edges and find the edges where U and V are connected by the same edge. And if I do, then it's adjacent. And if I don't, then they're not adjacent. So there's quite a lot of work here. We've got to search through this entire list. In the case of the matrix implementation, the adjacency matrix, all I would need to do is just check. If I'm looking if A is adjacent to B, all I need to do is see if there's an edge here between A and B. So I look at the numbers. This is a 0, this is a 1, 0 and 1 is a true. So they are adjacent. So that's O1 complexity. That's very cheap. Very cheap indeed. Okay, I think I messed that up. Right, I hope you can see the slides. So the rest of them you can do on your own, but actually let me just try to help you with just two more. So the insert vertex, this one's a bit tricky. So for the edge list, it's very easy. I would just insert it into this list. If I want a new vertex, I just extend the list by putting a new vertex in here. If you have it as a linked list implementation, you can do it in O1, which is constant time. In the case of a adjacency matrix, looking at this, if I wanted a new vertex, suppose I want to do a new vertex, I don't know, let's call it Y. I would need to extend this entire matrix one more. And because it's contiguous, because we're dealing with contiguous memory, I would need to redefine a brand new matrix. A brand new matrix with now, instead of 4 columns and rows, it would need to be 5 columns and rows. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, and because it's contiguous, I can't just extend into memory. I need to redefine the matrix. So not only do I need to redefine the matrix, but now I need to go to each and every one of these cells and copy the information perfectly from this adjacency matrix into this adjacency matrix, the new one. And then I still have to deallocate this one. So the total complexity here is n squared. Now it's quite a lot, right? I mean, n squared is a lot if you have a lot of edges. So that might be a big red flag, right? Inserting a vertex might have a big red flag, okay, for the adjacency matrix, because that's a lot of work compared to O1. Finally, inserting an edge isn't difficult, because inserting an edge in an adjacency matrix just means that we're going to index a cell and insert an edge. But inserting an edge into an edge list means that we would simply go extend this by one more and then mention the vertices that the edge involves. As simple as that. So it's O1 as well. Erase vertex, the same story. I would need to search all in the edge list. I would need to search the entire list of edges and find all of the edges that involve the vertex V and remove them. And to erase a vertex in an adjacency matrix, my goodness, that's a nightmare. We would have to now redefine a smaller matrix, copy all of the information from the big matrix to the small matrix, and then, because we are working in C++, deallocate the big matrix, and then keep the small matrix. Erasing an edge is much easier because, remember, in an adjacency matrix, we're simply indexing a two-dimensional array and changing it to null. So erasing an edge is easy. And also, erasing an edge is also easy for an edge list, because all you're doing there is removing the edge from the list. We don't really mind, because all of the information on the edge is isolated so that we can just scratch it out. So that's how we would compare the performance between the edge list and the adjacency matrix. I hope this lecture was useful, and by now you should know how to represent graphs, how to implement them using edge lists or adjacency matrix, at least conceptually. There is an assignment question where I ask you to use graphs. It's the last assignment question. And if you feel you're comfortable enough to tackle that problem with graphs, then by all means do so. If you use other data structures to solve that problem, I will in no way penalize you. But I would like to see some graph-based implementations from you. So because of the lockdown, I haven't really been I've been much more lenient about how students tackle problems. Just simply because of the spaces we're working in and the environmental factors. So also the lack of lectures. I'm sure a lot of you must have been very disappointed that we don't have face-to-face lectures. Well, so am I. That's something I enjoy tremendously. But it is what it is. We just have to make do. So like I said, there is a lot of online support for everyone, and I would like you to use it. There's so much of support. You can email your teaching assistants directly, as well as you can email me. You can also post questions on the forums. You can form your own study groups. You could have group consultations as well. There's the weekly consultations on Mondays run by the teaching assistants. So there's lots of assistance for you. Okay, even though we're not having face-to-face classes, there's a lot of other support offered this year that hasn't been offered before. Yes, so I think this is the last week. So I don't know if the tutors will be working during the exam period. I don't think so. So I invite you to try to get through as much of the coursework and ask as many questions as you can in this week so that you'd be better off. Okay, thank you very much.